Good morning. My name is Jelle Goeman, and I will tell you about the analysis of neuroimaging data using true discovery proportions. I will talk about what true discovery proportions are and about how you can interpret them. I will also explain how they help to solve the spatial specificity paradox that the previous speakers introduced. Analyses in terms of true discovery proportions are more flexible and more informative than classic cluster inference, but they have just as rigorous error control. From the previous speakers, you have heard that classic cluster inference in neuroimaging actually makes very limited statements. The only thing we can say about an active cluster is that it contains at least one active voxel. Such a statement is useful if the cluster is small, but it is almost meaningless if the cluster is large. This is the spatial specificity paradox. For proper interpretation of significant clusters, we need to say a bit more than that. We want to be able to say what proportion of the voxels in the cluster is active. This is the true discovery proportion. It is the proportion of voxels in a cluster that is truly active. It is abbreviated TDP. Every brain region has its own TDP, not just clusters, but also anatomical regions. And the entire brain also has a TDP. If we analyze our data in terms of true discovery proportions, our goal is to find brain regions for which the TDP is high. And ideally, of course, such regions are also large and meaningful. Since we do not know which voxels are truly active, we cannot just calculate TDP for brain regions. But we can calculate a lower 95% confidence bound for the TDP of each region. This is what TDP methods return. The guarantee of TDP methods is that the true TDP is larger than the confidence bound with 95% confidence. The TDP bound is therefore a conservative estimate of the true TDP. These confidence bounds, moreover, are simultaneous over all subsets of the brain. Simultaneous means that with 95% confidence, all confidence bounds are simultaneously correct. Simultaneity is a very useful property because it implies that the confidence bound remains correct even under data-driven selection. That means that if you have chosen your brain region in a data-driven way, the TDP bound is still lower than the true TDP with 95% confidence. And if you report more than one brain region, you have automatically family-wise error rate control. This family-wise error rate control is a consequence of the simultaneity. So what does this look like in a concrete example? Suppose we start from a classic analysis with a few clusters of voxels with a z-score statistic over the threshold of 3.2. Rather than a p-value for these clusters, we get a true discovery proportion bound. For example, we see that cluster A, consisting of over 2000 voxels, is at least 29% active. Cluster B, which is slightly smaller, is even at least 46% active. Other clusters, such as D, do not show any significant activity. But the analysis does not end here. The TDP of 29% indicates that cluster A is poorly localized. We had better look at subclusters with a better localization. We can do that by increasing the z-score threshold, say to 4. We see that cluster A in this case falls apart into 3 smaller clusters. Cluster A1 of about 400 voxels has a TDP of at least 66% and localizes the signal much better. Making clusters B and C smaller even leads to larger clusters with even better TDP. We can play around with thresholds and clusters as much as we want. The final clusters we choose and their TDPs are not compromised by this search process. We retain 95% confidence for all these statements. So how does this shed light on the spatial specificity paradox? We look for brain regions with high TDP. Such regions have widespread signal. If we find a large region with low TDP, we can attempt to zoom into smaller subregions. If these regions have higher TDP, we have localized the signal better. If not, then the original region has weak or scattered signal that cannot be pinpointed. TDP inference can be used to look at all brain regions. We do not need to commit to excursion sets or to anatomical regions of interest. We can simply look at both. If we look at excursion sets, we do not need to choose the threshold before seeing the data. If we look at anatomical ROEs, we do not need to choose an atlas in advance. We can even let the TDP itself decide what brain regions to look at. For example, the largest possible regions with a TDP over 70%. And even that 70% is not set in stone. We can adjust our target TDP after seeing the data. TDP inference brings its own terminology, which can be confusing at first. But this terminology is closely related to the classic terminology that you are used to. Remember that a significant cluster was a cluster of which we are 95% confident that it has at least one active voxel. This is the same as a cluster with a TDP bound greater than 0. If a cluster is voxel-wise significant, that means that we are 95% confident that it contains only active voxels. This, in turn, corresponds to a TDP of 100%. All other values of TDP, therefore, represent a continuum between cluster-wise and voxel-wise significance. Similarly, as I have explained, family-wise error control and simultaneous confidence are mathematically equivalent to each other, so the error rates are just as stringent. Next, I will explain how TDP bounding methods operate. They are all based on an underlying principle called close testing. Close testing uses as building blocks tests for the presence of signal in every brain region and turns these test results into TDP bounds. Let's look in more detail how this works. For simplicity, I will use as illustration a tiny brain consisting of only 4 voxels. Here it is. The voxels are numbered 1 to 4. First, we list all subsets of the brain. There are 15 of them. 4 of 1 voxel, 6 of 2, 4 of 3, and the entire brain. Note that we look at all possible brain regions here, also disconnected ones, such as we see for the 2 in the middle. Next, for each of these 15 regions, we do a test for the presence of any signal. I will discuss later what tests that can be. For now, the only thing that is important is that each test is valid for testing the region null hypothesis that the region contains no active voxels. The results are displayed here with a green check mark if signal was found and a red cross if not. Close testing operates under 2 inferential rules. The first one is that we are only confident about signals that are found in all supersets of a region. The rationale for this is as follows. Note that if a region has signal, then all its supersets must also have signal. So if we do not find it in all of these supersets, we are unsure about it. Close testing implements this inferential rule by discarding the significance of all significant sets that have non-significant supersets. In the example, the 3 sets at the bottom are subsets of sets that are not significant, so their significance is cancelled. All other sets have their significance retained. The second rule of close testing is that abundant signal is signal that is present in many subsets. To understand this with an example, imagine that a set has more than 50% active voxels. Then every time we split the set into 2 equal parts, we must have signal in both parts. The converse is also true. If all possible ways of splitting a region in 2 result in both halves having signal, then the region must have a TDP over 50%. This second principle is used by close testing to find the TDP of a region. Let us find the TDP of the region indicated in the title of this slide. To do this, we only need to look at the subsets of this region. Since the region itself is significant, we are 95% confident that there is at least one active voxel. This is a TDP of 1 active voxel out of 3 in the region, so 1/3. However, we see that also the subsets of size 2 are all significant. This indicates that there are confidently at least 2 out of 3 voxels active, for a TDP of 2/3. The subsets of size 1 all had their significance cancelled. If they would still all have been significant, we would even have had a TDP of 3 out of 3, or 100%. So closed testing is a general machine that takes tests for region null hypotheses and turns them into the simultaneous TDP bounds that we need for inference. Now let us look at concrete methods that use the closed testing principle. I will discuss two different choices for the region null hypothesis test. One, cluster TDP, is motivated by classic cluster inference in neuroimaging. The second, ARI, is motivated by classic multiple testing methods. We will see that the two methods both have attractive properties, but that they are also very widely different. What the two have in common is that we have developed fast algorithms so that they can both be applied easily on neuroimaging data. So, what test can we use to detect signal in a brain region? One way is to build upon classic cluster inference. We can say that we find signal in a brain region if that brain region would have given a significant result with classic cluster inference. So how does this work? We choose a z-score threshold before seeing the data, say 3.2. Next, we find the excursion set of all voxels for which the test statistic exceeds our threshold. This excursion set is not usually a connected set, but it falls apart into connected clusters. Classic cluster inference calls any such cluster significant if their extent, their number of voxels, exceeds an extent threshold k. This k, in turn, is determined using either random field theory or permutations. We can easily turn this procedure into a test for a region null hypothesis. We apply classic cluster inference on the region only. That is, we use a mask removing all other voxels. If that restricted cluster inference would find any significant cluster, then we reject the region null hypothesis. If next we feed this test into the closed testing machine, we obtain a method called cluster TDP. Cluster TDP is attractive for neuroimagers because it is so closely tied to classic cluster inference. It is just an extension of what people already do. Because of this connection, the results align perfectly. Every significant cluster gets a TDP in addition to the usual p-value. The TDP is always greater than 0 if the p-value is less than 5%, and it is always 0 if the p-value is greater than 5%. The method also shares the property of classic cluster inference that it is good at detecting clusters. It will find many clusters with a TDP greater than 0. A drawback of the method, however, is that it requires that the user specifies a z-score threshold before seeing the data. The method gives the best TDPs for clusters defined by that pre-chosen threshold. It is therefore not very good at zooming in and out. Also, TDPs for large clusters tend to be not so high, and it is quite difficult to get TDP higher than 50%. This is the flip side of the method's high detection power. The major asset of this method is that it gives a TDP for free with every significant cluster that you found. It can be added without any problems to any standard analysis. If we want to leverage the possibilities of TDP fully, we can use another test for the region null hypothesis. The SIMES test relates to the Benjamini-Hogberg procedure of FDR control in the same way that the test of cluster TDP relates to classic cluster inference. The SIMES test rejects the region null hypothesis if the Benjamini-Hogberg procedure, restricted to the region, would reject at least one voxel. What does that mean? We check whether the smallest p-value in the region attains the Bonferroni significance level of 0.05 divided by the number of voxels in the region. Next, we check whether the second smallest p-value reaches twice the Bonferroni bound, and whether the third smallest reaches 3 times the Bonferroni bound, etc. The p-values and their bounds are visualized in the figure below. If any of the p-values is smaller than the bound, that means we have found significant signal. The test can be embedded in a closed testing procedure. The resulting procedure is called ARI, for all resolutions inference. ARI is not as well aligned to classic cluster inference as cluster TDP. It may miss out on detecting some clusters that classic cluster inference would find. On the other hand, it is much more flexible because it is not tied to a specific z-score threshold. It is therefore much more suitable for localization of signal by zooming in and out. It is also much more likely to give high TDP values. So, compared to cluster TDP, it is less good at detecting, but much better at localizing. Let's wrap up. TDP-based inference solves the spatial specificity paradox of classic cluster inference. It does this by quantifying the extent of the signal and by allowing zooming in and out. It offers unprecedented flexibility. You can look at any regions you like and adjust your interests on the basis of your findings. Still, it offers as strict error control as classic methods. We recommend that TDP should always be reported with any significant cluster, because it offers a much better summary of the evidence of the region than a p-value. A results table of a neuroimaging experiment should look something like this, with the TDP bound given even more prominence than the p-value of the region. We have presented two methods, cluster TDP and ARI, so when to use which? We recommend to use cluster TDP as an add-on to classic cluster inference if you have done your standard analyses in FSL or SPM. You can use cluster TDP to add TDP to your results and get more information that way. But if you really want to exploit the flexibility offered by TDP-based methods, ARI offers you such flexibility. It is good at zooming in and out and localizing signal. We will see both methods in action during the practical this afternoon. And for more robustness and power, you can even use the permutation-based variants of ARI that you will learn about later in this course. That was all from me today. I will close with some selected references for those who are interested in reading more. You'll see references about TDP in general, about ARI, and about cluster TDP. The first two of these papers are a bit more accessible for non-mathematicians than the latter two.